This morning we're going to have the second talk of the two this week by Foteini Baldimtsi, who's one of our summer faculty fellows and a professor at George Mason. Foteini, all yours.
All right, thank you, Tim. So the plan for today is to talk about anonymous credentials, and I'm going to spend most of my talk actually giving you the background on the space and explain how anonymous credentials and anonymous authentication used to work in the past. And then towards the end of the talk, I'm going to kind of modernize things a little bit and discuss how decentralization can help in the space. So let me start for a second and have you all think about how many online electronic transactions or like digital transactions we now do. We use like the MetroCard to come to the office every day. We use cryptocurrencies. We use services like Netflix, social media, online storage services, and so on. And let's think for a second, how much personal information do we leak through all these services that we use, okay? And also pause back and think, how much information would you leak if you were paying for all these services with, for example, physical coins, or if you were not authenticating before accessing any of these services. So the amount of information that we leak is a lot. And even if we don't think that we're actually leaking information that can identify us, this is very often wrong. There have been studies that actually show that a very large percentage of the population can be uniquely identified by having 3 unique attributes like date of birth, gender, and zip code. So towards this end, there have been quite some policy discussions the last few years on how can we actually minimize the data that we provide online, both in the European Union, but also in the US, mostly in certain states, I would say. The main principle for these guidelines is that the collection of personal data should remain to the absolutely minimum that we need for whatever service we're using. So the question that we're trying to answer here is, if we want to retain our privacy, does this mean that we have to stop all these very convenient and nice electronic transactions? And the answer is no. Luckily, we have a lot of research and many cryptographic techniques in the space that can help us with that. We can use privacy-preserving protocols. And the main focus of today's talk, and I think a core focus for anonymity in digital transactions, is that of authentication. Because if you think about it, most of the information that we actually leak, it happens at the point that we authenticate in order to access a service. So what is our goal here? So let me start stating what we want by anonymous authentication. So ideally, we want to have users that have digital credentials that list a whole bunch of attributes like their name, date of birth, address, country, maybe some unique ID number. We want these credentials to be issued by some sort of legitimate issuer. You could think, for example, as this being like the state identity of ICE. And then what we ideally want is to use this credential, to use this information in a completely privacy-preserving manner. So let's think for a second what happens when people go to buy liquor today, right? So you walk into a store, like physically actually. You walk into a store and you show your identity card, and the information that you leak is so much more than what they need to know. So what they need to know is basically that you're over 21 years old. It doesn't matter if you're 22 or if you're 55. It doesn't matter what's your name, what's your address, or any of this stuff. So ideally, when we're building towards private anonymous authentication, we should aim for the for the best privacy that we can get. And the ideal goal here is that we should just literally be proving statements about our attributes that reveal the minimum amount of information that is needed for any type of transaction. So for example here, just that the age that is embedded in this credential is over 21 years old. Another crucial property that we want from such digital credentials is that we want the issuers of the credential to be unable to trace the transactions of the user. So this is not as easy in the physical world. So the state of New York, it's it would be very hard to try to trace you where exactly you physically saw your state ID. But in the digital world, if you just think of these IDs as being, like a series of bits, it's much easier to actually trace where this information is being used. So an ultimate goal of anonymous credentials and anonymous authentication is that whenever a user is using their credential, and this might mean that they either might, literally show the credential as it is, or show certain predicates, compute certain proofs on top of the attributes of the credential, this showing process should be unlinkable to the issuance process. So if the verifier colludes here with the credential issuer, they shouldn't be able to figure out who was the user that showed this proof. Additionally, even if the credential user creates more proofs to access other services as well, even if the proofs are on the same attributes, and here I'm conveniently bringing up an attribute that it's not unique, because if it was like the ID number, then maybe there is like an obvious uniqueness property there. That should also be unlinkable. Okay, so this proof should not be linkable to this proof, no matter who colludes, no matter who gets access to these, like verifiers, issuers, nobody should be able to link this together. Are the goals clear? Good. So, if you think about it, and if you ever took like a crypto class, you might already start thinking, how can we achieve these properties by known cryptographic tools? And if you, again, think of what are the properties that we want here, we want credentials to be issued in a way that obviously they should not be forged, I should not just be able to create fake credentials. And then if I want to do like proofs using some sort of privacy, it might become pretty clear to you that we might be able to construct some sort of generic constructions using digital signatures for the issuance of the credential, and then zero-knowledge proofs for the credential showing. The problem with this approach, although it technically works, is that it's not really efficient. Okay, so if you just try to randomly combine different types of schemes together, you're not going to come up with the most efficient constructions. And in certain cases of authentication, you actually really care about efficiency. So you should be able to access a service and issue a proof in like milliseconds. Even seconds are not acceptable. Okay, so we literally think of entering the subway, right? Imagine if everyone would have to sit in front of the entrance and take like 30 seconds to enter. Okay, this is not going to work.
So for the unlinkability property, if you use these generic, would you just like add a nonce or something like this so that you never?
Yeah, so basically we can just create a fresh zero-knowledge proof for everything that you do, for every statement that you show, and as long as these proofs are kind of re-randomizable, you can do that. Yeah.
So do you have any concrete numbers, like how slow it might be to use a generic CKP, like let's say bulletproof?
Yeah, that's a good point. I don't have concrete numbers, and nobody has, as far as I know. This might make like a nice, student project. But even if my understanding is that even if verification, could not, maybe it's not that bad, still computing the proof itself with, any sort of these like generic proofs, it's going to be pretty ugly. Again, we're talking about like milliseconds here, that would ideally like.
Why does the proof generation need to be that fast if you can kind of like pre-compute it?
That's a very good point. So you might not always be able to pre-compute it. So it might be the case that actually the authentication process is an interactive protocol with the with the entity that you want to authenticate. You might not know ahead of time what kind of attribute exactly they're going to ask for. It might be time specific. Again, like for the subway, it might have to be tied to the exact time that you're entering the subway, because maybe the charging policy has to do with how many hours you're using the train. So there are many parameters that generically you cannot just say that pre-computation is acceptable.
There's also issues with difference between time of use and time of check, or time of issuance and time of check, right? So I imagine that would be even more crucial here with the anonymity.
Right. So absolutely, yeah, there can be like timing issues. So the reason for, the reason that such generic constructions are not efficient, as I said, is if you just like plug in things together kind of randomly, it's very hard to make them compose well and nicely and very efficiently. And this is the reason that we actually have over I think at this point maybe like 30 years of research on the subject of anonymous credentials, which basically means that how can we build specific cryptographic primitives for this very particular problem. So very tailored and very efficient. So when we think about anonymous credentials, I like to kind of split them in two categories. The so-called multi-use anonymous credentials that are based on general signatures, I would say, well, with certain properties in some cases, and zero-knowledge proofs. And the so-called single-use anonymous credentials, which are almost exclusively based on a special type of signatures called the blind signature, and potentially zero-knowledge proofs, depending on what you're trying to show at the end. And as I said, there is a very, very long line of research. I'm not exhaustive by any means here, starting back in the 80s. At the same time, there have been quite a few efforts to actually commercialize, to implement those protocols by Microsoft, IBM and Microsoft consortium under a European project that later kind of spilled over Hyperledger Indy, and even Signal these days actually uses anonymous credentials techniques for authenticating users in groups when they're doing their messaging. So what is the difference between the two, and what do we prefer in each case? So the idea of a multi-use credential is that I get a credential issued once from the issuer, so I interact with the issuer once, I get like one object, and then I can reuse this object multiple times in order to authenticate. So naturally, multi-use credentials make sense in subscription services, or if I actually want to digitalize my state ID or my password. Single-use credentials are credentials that are literally issued and can only be used once. And as a matter of fact, if you use them twice, you might actually lose privacy. Okay, so you might be actually able to link them together. However, there are certain cases where single-use credentials is what we need. So, for example, you might want to issue some sort of like single-use coupon. You might want to issue, you're using this type of credentials if you want to build like a new voting scheme where you need to have like a ballot that you can only use once. And also single-use credentials naturally give what is called, or what we used to call in the space before blockchain, I guess, electronic cash. So they would naturally give this coin that you can only use once. The caveat here is that single-use credentials are actually much more efficient. And this is going to become apparent because the main idea is that you get a credential issued, you get a signature, and then during presentation, depending of course on what kind of statement you're proving, you might not even need to do a zero-knowledge proof. You might just literally show a signature, and presentation just literally means signature verification and done. So you're not verifying a proof, you're just literally just verifying a signature, and maybe the prover needs to do absolutely nothing, just literally present a signature. So I would even argue that in certain cases that you know that you're not going to use a credential many times, so let's say that I know that I'm only going to use a credential like 2 or 3 times, it might actually make sense to issue 3 single-use credentials instead of getting 1 multi-use credential. So it might actually be more efficient. So let me start the discussion with single-use credentials because I think that actually the techniques are pretty interesting here. And they were first introduced back in the 90s, and as I said, the core primitive is a special type of digital signatures that are called blind signatures. And for those of you that were here on Tuesday, you might got bored hearing me talking about all these different types of signature schemes, but I saved one for you today that I didn't cover on Tuesday, blind signatures. I could have easily put that on Tuesday as well because they are used in certain Web3 layer 2 mostly applications. But I wanted to save one more signature for you. So the core primitive is a blind signature, and I actually think it's a very interesting type of signatures, and I want to explain to you how they work. So when Stefan Brands defined single-use credentials, he used an elliptic F-based blind signature that was 3 rounds. And the problem with that scheme was that, and again, think that we're back in the 90s, people do not really have so formal security models, definitions, so they don't care about security proof so much. So the problem was that no security proof was given. And the interesting part here is that Microsoft on their digital identities project, uProof back then, was actually adopting the signature scheme. So when I started working as a PhD student, one of the first tasks that my advisor assigned to me was actually prove security of this scheme. She was like, well, people are talking about the scheme for so many years, it doesn't have a proof security. So, I I was trying really hard and I was failing. And at some point we actually came to a realization that it was kind of impossible to prove the scheme secure. So again, we didn't find an attack. We essentially came up with an impossibility result. We ruled out, in a sense, a number of techniques that one could use to prove the scheme secure. For the cryptographers in the room, we did that using a technique that's called the meta reduction. So we said that if there is a way to prove the scheme secure, then you can break a hard problem. Okay? So again, this is not an attack. We're not saying that the scheme is not secure, but this is certainly an issue, right? We're not, as cryptographers, we're not so happy to implement and use schemes for which security is unclear.
And so, Foteini, the meta reduction was for proving security in a particular way, or?
We were ruling, the way that it works, we're pretty much like ruling out many ways. So it's not like one particular way, but
Gotcha. I'll ask you off.
yeah. So we're ruling out, like, we were even saying, our meta reduction says that even if you assume that the scheme itself is secure, you still cannot prove it's secure, which is kind of fun.
I want to be more.
Yeah, so meta reductions, I think, we've seen meta reductions for different primitives in crypto. The last, like this sort of impossibility result, meta reductions for different primitives in crypto the last years. And something that I should also note here is that actually blind signatures are a type of signature scheme that is notoriously hard to prove. And there are many subtle details when trying to prove security, and I'm going to come back to these topics. And after we realized actually that this scheme was not secure, was not provably secure, we actually came up with a scheme with very similar efficiency that we could actually prove it secure. So let me give you a high-level idea of how blind signatures work and how we can get anonymous credentials from blind signatures. So the idea of a blind signature is kind of untraditional to the regular signatures, that you have a user that has a document and has the signing keys and just signs the document. Instead, you can think of a blind signature as a two-party protocol. You have a user that has a document, and then the signer is a different entity. So what is the goal? The goal is that Alice wants to get a signature on her document from the signer, while hiding the message from the signer, while having unforgeability, so Alice should not be able to compute signatures that verify under the signer's public key alone. And at the same time, we also want unlinkability, which basically says that if the signer, at the end of the signing process, sees the final signature, it cannot link that, it cannot connect that to the signing process. So it doesn't know that this is a signature that was issued to Alice. So in a very high level, the idea is that Alice can take the document, put it in a box, lock the box, and you can think of this as being some sort of a cryptographic commitment here, so Alice can commit to that, have some secret randomness that was used for the commitment, send this committed document, this hidden document to the signer. The signer, using its secret key, is going to compute a signature that I call sigma star on top of this hidden message, send the sigma star back to Alice, and then Alice, using sigma star and the randomness that used in order to hide the message, can actually unblind the signature to a signature sigma that will verify under the signer's public key for the original document, not for the committed one. So we need a minimum of 2 rounds for such blind signature protocols, and I hope that this becomes clear because the user needs to send something to the signer before the signing process starts. And the efficient protocols that we have in the space are actually 3 rounds. Okay, so we have some constructions in 2 rounds that are not as efficient as we want here. So now, again, the important part is that obviously Alice cannot create signatures herself, but also if the signer sees the signature sigma in this document, they cannot link it to the signature sigma star that they created here. They look like 2 completely different signatures. So how can we use these signatures now as a means of anonymous authentication? So let's say that Alice wants to provide this credential to some verifier. You could think, for example, of this as being some sort of token. Think the Uber codes that Claire sends us whenever we go out one night. So we have this like one-time token. We want to use it to some verifier, Uber, let's say. So what we can do is that we can literally just present the signature and the message that says this is one free ride, and the verifier will just verify that the signature verifies under the signer's public key. And again, the nice property here is that even if the verifier and the signer colludes, so even if Claire colludes with Uber, she shouldn't be able to find out how we travel, how its users use their one-time coupon, their one-time code. Okay?
Quick question.
Yes.
So to do the unblinding, you need to know both like the original document and the randomness? Or what was
Yeah, so you needed to know the original document because the signature will verify the original document, and you typically need to know how you blinded this. So basically, again, in a very high-level way, you're blinding the document, so the signature is also kind of blinded under the same randomness, and then you somehow kind of divide out this randomness, and you have like both the unblinded message and the unblinded signature, again, in a very high level. So something that we have to be careful about here is what happens if the user is malicious and tries to reuse the same one-time token. So here the problem is that ideally what should happen is that the verifier should be able to reject this token because it has been already used. And unfortunately, the only way to do that is to literally maintain a list of all the used credentials, of all the credentials that we have seen, and make sure that this doesn't appear there. Okay? So there are certain techniques to avoid holding this list that, you know, might become very large. You might have expiration dates in the credentials, so you might have, you know, like credentials that only last for a week or a day or a few hours, so that you don't really need to hold anything that has expired. So the way that I presented credentials, this like single-use credentials so far, I didn't talk about attributes at all, and this was something that we really cared about. I just said you have this like one-time token that we literally just want to show it, and that's why I said that at this point this was super efficient. You see, like during showing, the user did absolutely nothing, like zero computation. Literally just presented a signature, they verified the signature, that was it. Well, if you start adding more complexity in the system now, if you start adding attributes, things will also naturally become a little bit more complicated, both during the issuance process, but also during the verification process. So now think that in this like one-time token, we also want to add attributes for the user. So we might want to add, I don't know, like the secret key hidden in there, the name, the date of birth, or something like that. So the idea here is that, so now the methods might become more complicated, or in certain cases you could actually think of the attributes as being like a second message concatenated with the message that you're actually signing. So maybe a simple way to think about this is literally think of this as like coins, digital coins. Think of the message as a unique serial number, and then think that you're also attaching a bunch of attributes. Why is this useful? If you use these coins, let's say, to enter the subway, you might be able to show that you get like a senior discount because your age is over, I don't know, 60, whatever it should be. And you might want to actually have this like more rich credentials that have more information, even if they're single-use ones. So the idea there is that you can start by committing to your attributes. Potentially, you might need to include a zero-knowledge proof that whatever you committed into here is correct. And in certain cases, you might need some sort of physical means to do that. So you might literally need to show like a physical identity to prove to the issuer that, yeah, like whatever I'm putting in the commitment are, you know, my true attributes. And then the challenges now are you want to create a blind signature on some message that also includes the commitment. If you just literally sign the commitment, this is going to get problematic. Why? Because we cannot just rely on the user to randomize the commitment, because maybe the user will randomize the commitment in an anonymous, in a malicious way, and add different attributes from the ones that actually the signer verified that are correct. So if we just consider C as the message that we had before and allow the user to hide it, who guarantees that the user is just not putting different things in there, okay, if it's completely hidden from the issuer? So the challenge here is to actually create a blind signature scheme such that the user and the signer jointly randomize C in a way that the final signature will be on a C, on a commitment that the signer doesn't know, but at the same time, the user cannot just change the committed attributes. So to achieve that, we defined a variation of blind signatures that we call blind signature with attributes. And things there get quite more complicated. I'll actually show you how it works. But again, like the high level idea is this joint randomization of the commitment in order to issue the signature. So at the end, what Alice gets is a credential, sigma, a signature, on a randomization of the commitment C on the attributes, C prime, such that it was created in a way that it guarantees that are the same attributes included as the ones here that the signer verified, but also in a way that guarantees unlinkability with the C that the signer knows for this commitment, for this user. And if you think about it, you could literally think of this phase as being some sort of like a one-time registration phase. So if you think of this as ECAS, you can think of the issuer as being the bank, that you register once, show your full credentials, open your account, and whenever you go to your bank to get one-time tokens, one-time coins, you just run this phase. So you basically keep on re-randomizing these commitments. Okay? And potentially the bank, will be crossing out coins from your account. Does this make sense? I know that these are quite complex ideas if you've never heard about them. Yeah? Okay.
Is it easy to say in a sentence or two a little bit more what like jointly randomized means, like concretely?
Mm-hmm. So, literally what happens here is that, again, think of these as like 3-round protocols. So the signer starts by randomizing the commitment. If these are Pedersen commitments, for those that they know that they're based on like discrete log, literally the signer can pick some randomness and put it on the exponent of the commitment. And then this is sent to the user. The user is going to add some additional randomness. The point there is again that you want to make sure that the user is randomizing whatever it got from the signer and not something new. So the signature will only go through if the committed message is a randomization of what the signer computed. So it might not know what was the second randomness factor used by the user, but it has to guarantee that it's just like adding extra randomness on whatever the signer started with. Because again, if we allow the user to completely randomize things and do whatever they want, they might just put different attributes there that they're not valid. So it's actually, it's pretty tricky. I mean, this, again, for the cryptographers, I guess, in the room, these blind signature schemes, in a sense, work as an OR proof. So the user is, well, the signer is actually either proving that knows the secret key or that knows this like randomization. So they're kind of pretty involved to come up with. So on top of the properties that I was mentioning before, like enforceability and unlinkability, obviously what you want here is that when you open, if you open these credentials, these commitments shouldn't be able to open to different attributes. So here, when you're using these now tokens, these one-time credentials with attributes, when you present them, if you just want to present them as a one-time token, I have like this one-time access. Again, as before, you might just literally reveal the signature on the message C prime. And, or if you need to do some sort of partial opening, the nice thing about these commitments is that there is a very easy and efficient way to just open one of the attributes. So just show the age and nothing else. Or if you don't even want to show the age, but show some sort of predicate, like my age is over 21 years old, add some sort of zero knowledge proof on top of that. Okay? So having that, of course, like you cannot avoid the zero knowledge proof here if you want to do some more complicated proof. Again, the properties should be that these are unlinkable, so no matter how many accounts the signer controls, no matter how many commitments the signer knows, and how many tokens it has created, it shouldn't be able to link any presentation of these credentials. And of course, like we should be like mindful about privacy here. So if an issuer has a single user that is over 90 years old, then obviously they can de-anonymize it, right? So you should always think that the level of anonymity that we get here is some sort of set anonymity on other people that have the same or similar sets of attributes as you. So as I said, we came up with this nice scheme that we called Anonymous Credentials Lite, and it kind of stayed the state of the art for many, many years. The scheme is, besides having these like 3 rounds, it is based on LP curves, it's relatively efficient, it just has like, it's discrete log based, it only has like a number of exponentiations. But the thing that I want to highlight here, again as a cryptographer, is that the security proof that we had for the enforceability of the scheme, it was only working in the so-called sequential setting. So we're saying that our scheme is unforgeable, it's impossible for an attacker to forge proofs, as long as the issuer was issuing one proof at a time. And again, remember that these are interactive protocols. So if you think of the issuer as being some sort of server in real life, you might actually want it to have multiple signing sessions open with multiple users. But we didn't manage to prove security and the parallel composition, we left that as an open problem. So almost 10 years later, we actually had an attack, okay? So there was a very nice paper that came up and said that many blind signature schemes, mostly discrete log based, but not, well actually yes, mostly discrete log based, are not secure under parallel composition, under parallel issuance. So this was a concrete attack, this is not some sort of impossibility result. It literally said that if there is over a threshold of open issuance sessions, then we can actually forge signatures. Okay? So this was pretty annoying.
So
yes.
So you're saying, like, consider the existing signature schemes and consider just naive parallel composition, when you just still have
Yeah,
3 rounds.
it was not naive. The technique was, actually using some like math. So they literally showed an attack that said that if you have like multiple issuance sessions open, so if you have started interacting with multiple users for multiple messages, so think of this as some sort of like linear composition, so it's some sort of like linear equations. If you combine all the information that you know from all the open signing sessions, combining all them together allows you to create a forged signature for something else.
So it's not even like you need them to be proceeding in tuples, like back and forth in sort of lockstep.
No.
So you're saying if you can pull the information from all of them, then.
Right. So if you're like a network attacker that you're observing what's happening and you have like all these sessions open, and again, I mean, you need like enough sessions to be open, but again, the parameters would depend on every particular scheme. But yeah, you could like some sort of linearly compose all the information that you have and manage to forge signatures. And again, this is not just like an impossibility thing. They didn't just say that security is impossible in the parallel setting, they actually saw an attack. Okay? This didn't violate anything with our proof, for example, or other proofs, because our proof was only in the sequential setting. We never claimed security in the parallel setting. But this is something that actually raises concerns about how to use these schemes in practice.
So how did you use the facts? How does the proof use the sequentiality? Like, is there some way that like one signature depends on the result of the previous one? Or?
No. So basically again, the reason that this attack works is that, so these protocols are usually 3 rounds. So they use the first 2 rounds of every open session, not the 3rd one, in order to conclude to a 3rd one, like a closing one that works. So if you do it sequentially, if you close every single session before you move to the next one, then you're not able to do that. But if you're able to interact with the signer in a way that you can mold things by using other open sessions at the same time, then you can come up with a forgery.
Is it a semantic security issue where you're using like some sort of, because you're talking about aggregating it and are you doing like pattern analysis on it, or?
No, it's actually, it's a mathematic-based attack. It's called the Ross problem. I can give it's pretty technical. I can give reference and tell you more about it. And again, it doesn't only affect that particular scheme, it affects many blind signature schemes. And as I said before, it's like proving security of these blind signature schemes, it's actually extremely hard. It's it has like very, very particular techniques.
I have a similar question. When you say you have an attack, do you break the zero knowledge, or you break the, like there are multiple parts. You break
So you break unforgeability.
You break the what?
Unforgeability. You can forge signatures with this attack. Yeah. So it was like the unforgeability that is being broken. Yes.
So in the previous slide where there was a ZK proof required, so what happened to the efficiency concern that this was supposed to solve?
Right, so that you cannot avoid if you want to do more complicated protocols here. Still, there are structures in signature elements that compose better or worse with zero knowledge proofs.
So the partial opening is like revealing age fully as
Good,
opposed to
yes.
like-
So if you literally want to reveal age and not show some predicate over your age, actually you can do that very, very efficiently. So no need for zero knowledge proofs. You just very, very efficiently can open part of your commitment. If you want to prove something more complicated, some sort of range proof, for example, in your age, that you're between some range or over some threshold, this is where you would actually have to do a zero knowledge proof. But again, just literally opening one predicate, it's very, very efficient. So in practice, actually, when people consider these single-use credentials, they really try to avoid zero knowledge proofs. So they would literally, for example, for the senior discount in the subway that I mentioned before, they would model this as a binary attribute, 0, 1. So you would literally just open and not do any sort of zero knowledge proof. But again, this is like very application specific.
Are you going to talk about how to make it concurrently composable? I guess it's like theoretically it's well known how to do that.
Actually, I'm not. I don't have slides. We have some work in progress on that. It's not complete, so I cannot claim that we've done it yet. What we know is that there have been some recent works, I believe Eurocrypt 2022, that gave some efficient blind signature schemes using the AGM model. It's by Stefano Tesaro, that are parallel secure, that avoid this attack. However, they do not support attributes. They don't allow you to do this like double-side randomization of the commitment. So we currently have some work on that, but as I said, it's not complete so that I can claim that it's so.
So the main challenge here is to make it efficient, right? I guess theoretically it's
Yes,
not-
so, right. So we do have blind signature schemes that are do not suffer from this attack. They're in the standard model, but they're not efficient. So we don't have like discrete log-based, random oracle-based efficient blind signal. Well, we have this very recent work, as I said, like Eurogroup 2022. But again, it doesn't support attributes, so it's not direct. So it's not direct that you can just take any blind signature scheme. We don't have any sort of generic compiler to compile any blind signature scheme to a blind signature scheme with attributes. So this like joint randomization of the message that's being signed, it kind of needs to be embedded on how its protocol works. So we don't know how to do that generically.
I guess theoretically you can, like if you're not worried about efficiency, you can just use like a zero knowledge protocol.
Yeah. I mean, you could
and not malleable.
completely solve this problem by just taking a zero knowledge proof and a signature scheme, but here we want to avoid zero knowledge proofs completely. Yes.
So when you say efficient, does that like kind of just mean less exponentiations, or like a technical definition of what's efficient and what's not?
Yeah, I don't have a technical definition, but yeah, so we basically, we just want like a few exponentiations or a few point multiplications or just a couple of pairing operations, and also we want short sizes of all this stuff. So this concludes my discussion on single-use credentials. So this is a topic that I think it's actually open at this point. We don't have an ideal single-use credential scheme with all these properties that I mentioned. We have some work in progress. Talk to me offline if you want to hear more about what we're trying to do. I'm happy to explain. Going back to the multi-use setting, I'm gonna say a few things here in a much higher level. So the core primitive here for multi-use credentials were again a special type of signatures, but not maybe as complicated as blind signatures, and not like completely different definitions here. These are the Kamenisch-Lisianskaya signatures, which are basically signatures and committed values that allow for efficient proofs of signature ownership. So efficient zero-knowledge proofs on top of the signature. So signature schemes tailored very, very specifically for efficient zero-knowledge proofs. So the original CL signatures were based on RSA, so they were pretty large and they had some expensive operations. later works gave signatures with similar properties that are based on elliptic curves and bilinear pairings. So for those of you that know things in the space, this is what we usually call the BBS plus signature. So again, signature with similar properties, but more efficient. So the idea of these multi-use credentials is more similar to the generic constructions that I was mentioning before. You have a commitment to your attributes. You start with, again, some sort of phase that you have to prove that what you have is correct. All these credential systems need some sort of bootstrapping, need some point of, actual truth on how to start. And then you get one of these special signature schemes that allow efficient zero-knowledge proofs. The high-level idea is that you're able to randomize the signature schemes multiple times. If you just want to solve the credential without proving anything about your attributes, literally you just need some sort of randomization. That's still more expensive than single-use credentials that you just literally solve the credential, you do zero, or you do nothing, you literally just solve the signature. Here you have to keep on randomizing them because you want to maintain unlinkability with the signer. No matter how many times you use the signature, they should not be linkable. And as I said, you can repeat that multiple times for the case of multi-use credentials. There has been, again, like a lot of research in the space and many extensions here. For example, things like conditional anonymity. You can identify misbehaving parties under well-defined conditions. Revocable anonymity, how can you, using some sort of third party or threshold techniques, can you figure out who was a user? How can you delegate these credentials? I have a credential, I'm going to be on vacation, can I delegate it to one of my employees, for example? How can you use consistent pseudonyms across different services? There have been certain optimizations in the case that the issuer, if you know that in a specific setting the issuer and the verifier is the same entity, you can actually have much more efficient schemes. And there have also been schemes that actually use trusted enclaves to optimize certain things and get some additional results. Yes?
Are there ways to do non-repudiation without revealing the identity here, or?
So, without revealing the identity.
So I imagine like the revocable anonymity, one of the applications would be non-repudiation, right? If someone's trying to claim that they didn't assert something.
Yeah, so right, but the challenge is always there. How can you do that without just relying on a third party that has the tractor to just open up the identities of users? So I guess like the first two bullets are kind of connected, right? So in one hand, maybe you want some sort of specific policy that automatically is going to revoke anonymity without the involvement of a third party. While in the second case, you might actually involve some party or some threshold, some committee of parties. Yeah.
So you mentioned the revocable anonymity. What about just you don't want to revoke someone's anonymity, you just don't want their credential to work anymore? Revocation?
Yes, revocation is a very important problem, and it's actually one of the things that makes these credentials pretty hard. So credential revocation is a hard problem even in the non-anonymous setting. Okay, so just think of like certificates, like TLS certificates, right? How can we make sure what has been revoked and what not? And even like specifically again for the case of TLS certificates, our solutions are not great, are not completely online. It takes time to figure out what are the accept lists and revoke lists at any point. So and there is a lot of research in the space as well. So when you're adding privacy in the picture, everything becomes even more complicated. Okay. So I had actually planned to show you exactly how revocation works, but I think I'm gonna skip it so that I'll try to keep I'll say a few things, but I will not show you the exact solution, so that I'll try to keep the talk in 1 hour. And if people want to stay longer just to discuss revocation, we can do that at the end. So again, the high level of credential revocation is that you might have like an accept list of credentials. For simplicity here, I'm just literally throwing the names of the users, but you could think of this as being credential IDs. And if you literally just keep like a list, it's super easy to do additions and deletions, especially if they're under central management. But the problem is that the size of this list is linear to the number of users that you have there, the number of credentials that you list, and it's very hard to support user privacy. So the most prominent solution, in my opinion, for efficient revocation is a special type of cryptographic data structure, I would call it, that's called accumulators. And cryptographic accumulators are basically a way to compute a very short digest of a large amount of a large set that is actually constant to the number of elements that are included in the set, and still be able to compute proofs of membership or non-membership that ideally are constant in size. So you could think of Merkle trees also being some sort of accumulator. The digest of the set is just like the root of the Merkle tree, that's constant size. But still the problem with at least Merkle trees is that the proofs of membership are not constant size, they're logarithmic, okay, because they're like the paths in the tree. So accumulators can actually offer trade-offs when compared to Merkle trees to have, and the most important one is that the proofs are of constant size. So I'm not going to show you exactly how things work. I have like the example of the RSA accumulator. I just want to mention a caveat of accumulators that it's important. The thing is that when you add an element to the accumulator, you have a way, you receive some sort of short proof, short witness that we can use to, as I said, very efficiently prove membership or non-membership. The problem though is that when more elements are added on the accumulator, you have to update this proof. So technically, in the older accumulator constructions, you would have to update this witness both when additions happen and when deletions happen from the accumulator. But we have certain lower bounds and newer constructions that actually achieve them. And you can manage to have accumulator constructions that only allow you, that only require you to update your witness when deletions happen and not when additions happen. So if you think that you're storing credentials, you could potentially think that it's more often to add new credentials than deleting ones, and in that case, these constructions make more sense. So we have a series of work on that. Again, keep in mind that in these types of accumulators, there is some sort of accumulator manager, so there is some sort of third party that holds the accumulator, okay, that is responsible to maintain the accumulator. So in the last 10 minutes of the talk, I want to switch gears a little bit and give you like a high-level overview of what happens in the decentralized phase by talking about digital credentials and anonymous digital credentials. Again, I think that we see two types of approaches in the space. The first one is to literally take anonymous credentials as we used to know them in the past and decentralize parts of the process. So the main part of the process that you want to decentralize is actually the issuance process. You don't have a single issuer to vouch for a credential, but you might want to have more. The second approach is to kind of take issuers completely out of the picture or partially out of the picture and have users that create their own digital identifiers that they're not like centrally managed at any point. So this blends well with what Andrew was discussing yesterday about reputation systems, so some sort of like a web of trust idea that people create their credentials and then they can get, kind of some sort of distributed vouching of their credential, but without having some sort of starting point with a specific issuer. So I'm just going to say a couple of things about what do we know in each case. So in the decentralized issuance case, of again, like taking classic anonymous credentials and decentralizing them, the idea is that you might want to have multiple issuers working together to issue a credential for a user. One of the most prominent schemes is the Coconut credential scheme, where actually Sarah is one of the co-authors and is being used on the NIM project. So the idea is to use a threshold blind signature. So these credentials are actually kind of single-use credentials. The nice thing is that you can, as I said, you can thresholdize the issuance process. You can start by having a system where you define a number of potential issuers, let's say n issuers, and then for every new credential require that the threshold of them, say P of them, sign your credential. So the nice properties of threshold signatures, and for those of you again that were on my talk on Tuesday, might already remember what are the good and the bad things about threshold signatures, is that you get signer privacy. So you're not going to, when you see a credential, you're not going to know who were the issuers that vouched for this credential. You just know that this credential was vouched by enough issuers. But the problem is that the process of like setting up this set of issuers is actually kind of annoying. So in these threshold signatures, you need this distributed key generation process that needs to happen in order for them to agree on their initial keys. And this is a non-flexible process. If you want to add new issuers or if you want to remove issuers, you have to rerun the whole process. Also, it's not very clear how to efficiently add attributes in those schemes. There are ways to add attributes, by using like different public keys and kind of more like ad hoc ways, but they're not truly embedded in the system. So in a work that we actually have under progress, and again, I'm happy to talk with people about this, with colleagues from UMD and CISPA. We are trying to construct a similar scheme that instead of threshold signatures uses multi-signatures. And remember that the main advantage of multi-signatures is that they do not need this coordination among the issuers in order to create the credential. They have other issues, they're larger, and they also reveal who are the issuers, who are the signers of each credential. So this can be considered a feature in certain cases. So in certain cases, when you see a credential, you might actually want to know exactly who vouched for it. But in other cases, it might also be considered like a privacy issue. So it really depends on what's the application here. So the last thing that I want to mention, and then just kind of open the floor for discussion and mention some challenges, is the idea of decentralized identities. So the main idea on this whole space is that people want to change the way that we authenticate. Instead of using password authentication, we want to use cryptographic keys, like user wallets, to be able to authenticate. There are efforts like signing with Ethereum, or efforts like the Can We Do Decentralized Identities, which is again a research work that Andrew is one of the authors. Is Elaine too? I don't remember. Sorry. And the idea there is that, again, it's not like taking traditional anonymous credentials and trying to decentralize them. It's mostly like I'm a user, I have some information that I want to use in the space to start authenticating. They have some very, very interesting ideas on how can you bootstrap using oracles like Deco to transfer knowledge about your keys, your identities from other places. They have some nice accountability extensions. The level of privacy that these schemes offer are not to the point of anonymous credentials. So if parties start colluding with each other, you can actually de-anonymize users. And also, revocation is not, again, very efficient if you want to do things in privacy. And again, as I said, revocation is a crucial point here. Something that I want to mention now that I mentioned revocation for the decentralized setting, remember that I said before that using these accumulators to do revocation in the centralized setting, assume that you had somebody that holds the accumulator. You had like this accumulator manager. If you try to decentralize that, if you try to remove the accumulator manager and have a distributed accumulator, then things become much more complicated and much more expensive. So you actually need to hold the whole accumulated set to be able to compute proofs. So this is another like open research problem on how can we actually have efficient accumulators that are completely distributed. Yes?
Just out of curiosity,
Yes.
The practical applications of these decentralized identity, are there any projects that are building some applications?
Yeah, so
What is the main
NIM is building this idea of like thresholdizing anonymous credentials. And I don't know about the status of CanID. I don't know if you know, Andrew, what's going on there.
Do they have some application in mind when doing that?
Yeah, so I think NIM actually cooperates with certain parties in the European Union. I don't know, like governmental, I guess. They have some governmental access. And they're trying to build some pilots for like European identities or whatever. And yeah, for CanID, maybe Andrew.
This will be like a government ID systems?
Yeah, so I mean, again, Europe tried that before with this ABC for trust system before the age of blockchains. I guess early, or when blockchain was starting, maybe like 12, 13 years ago. But they didn't do much after the pilot finished. So I cannot really predict what's going to happen there, but I kind of feel that we're getting more ready for that. Also, in this space, NIM and Coconut were actually also using smart contracts for this thresholdized issuance of the credentials. So they were literally running this through a smart contract.
That's a good question. So one is, I mean, with NIM, what's the role of an identifier? Like, what do they use it for? I mean, I know that it's like a mixing network, or like a network layer. Like, why?
Yeah. So I think that like part of their system is actually building these digital credentials, and then they're using mixing techniques. It's like I think it's kind of like two different components there.
So for the issues with like the accumulators, the open problems that you mentioned, I mean, are these also things that are straightforward with generic zero-knowledge proofs, but it's the open problem to make them efficient, or is it difficult even?
So you mean if I don't use an accumulator and literally just use like a list of stuff?
I guess so, or some kind of.
Yeah. So this would, I mean, so I guess zero-knowledge proofs on top of accumulators is kind of a second step as well. So when you think about accumulators, you don't necessarily need to think about privacy-preserving proofs of membership. But what I'm saying is that even in the non-private setting, even if you just literally want to show non-privately that a credential is revoked or not, is in the list or not, in the distributed setting, we don't have great constructions so far.
Okay. Even with generic, I guess verifiable computing would be the appropriate.
Well, efficient, practical constructions,
okay.
Yeah, with generic techniques, yeah.
Right.
Yeah.
So by threshold, you mean that any of these parties can issue and you don't want to reveal who they are, right?
So yes, so what you want to do is you want to get a credential that was issued by many of these issuers, at least a threshold of them, without knowing who they are.
Is it, do you think, do you think maybe we can use advantage of some sort of multi-prover technique?
Yeah, that's what we're doing right now. Yeah, we're trying to use like multi-signatures. Well, I'm not sure what you mean by multi-prover though.
Oh no, I meant more like, we know that, say I have two provers and I know that they don't, like my assumption is that they don't collude, then that actually...
By provers you mean issuers of the credential, or... I mean, in my mind, these are the issuers and this is the prover, the user that has the credential and proves
Right,
things.
I guess yeah, you're right.
So
the user proves, right, it's not the issuers that provide proofs. Okay, yeah, then my question was
Okay. Yeah, so some final thoughts. Again, generic solutions exist for most of the problems that I'm raising. Efficiency is the big challenge. Think that many of these applications are real-time sensitive. You want literally milliseconds or microseconds. You might want to implement such things in lightweight devices, not even smartphones. If such things are implemented on the blockchain, like this issuance process or these credentials or these proofs are stored on the blockchain, you really care about sizes, storage, or gas costs if these are run through a smart contract. There is the bootstrapping problem, of course, and CanID had some ideas on how to start there. There is the big problem of accountability, which is a general problem with all privacy-preserving techniques. So privacy is great, but we need some sort of accountability if we want these techniques to actually be adopted. There is the problem of how can we do backup, how can we do identity restoration, particularly in the distributed setting if there's no trusted third party to help us. Revocation is a big problem, in my opinion. If it gets so expensive to prove that your credential was not revoked, it starts getting annoying. And I want to claim that basically post-quantum secure solutions are non-existent. Again, like efficiently in satisfying the goals that we have. So that's again a very open space.
So I had a question about kind of like the concept of anonymity that we were talking about here. So it seems like most of it was on the actual like message content, or I guess the message that's being passed back and forth, right? But wouldn't you also need some sort of oblivious routing or some kind of mixed network or something, right? If you were able to see activity. Just
so you mean like in network level?
Yeah.
Yes, absolutely. Yeah.
Right.
So I completely left like network level out of here, but you're absolutely right that even if I'm hiding all my cryptographic keys and cryptographic information, if I'm using like consistent IP, then of course like there can be like network level, and that's absolutely.
And have you looked at anything like autonomic identifier systems? So you were mentioning like the self-issued identity, right?
Mm-hmm.
So there's techniques where you can actually cryptographically issue like your own identifier without even anchoring it to like a blockchain or something, right?
Correct.
So
Yeah.
creating like delegated versions of those that are just like ephemeral, would that address some of the issues potentially, like from like a setup, I guess?
Right, but again, like you need some sort of bootstrapping. You need some point to start, right? So after you have this bootstrapping, after you start by getting some real life truth that these are your correct attributes, and you get your first credential, then you can really play along. You can like delegate things. You can get additional anonymous credentials on top of your already existing credentials that are unlinkable with each other. You can kind of keep on building on your digital identity, but there has to be some sort of bootstrapping, and I mean, to my mind, this is pretty natural, right? Somebody needs to literally verify your identity at some point. Again, if it's like just a secret key, for example, on Ethereum, and what you just need to know is that I have a key, I have an account, it's different, right? But if you want to start adding physical attributes, then you need something there. You need some entity, some trusted entity.
Are there like scenarios where just a timeout-based revocation works? Because that's kind of like, I guess, where
Yeah, absolutely.
going on the web.
Yeah, so you could, and that's something that I mentioned, for example. So this is more easy, I guess, to do in these one-time credentials, because they have like they can have very short expiration dates, so you don't even need to revoke them, basically.
Yeah.
For these consistent multi-use credentials, it's kind of harder to have expiration. I mean, you might have still, but it's kind of harder because you start building on top of them, as I said before. You use the credential to get additional credentials down the path. So if something expires at the root, then things might start going wrong. But even if you have expiration dates, you might lose your device, you might misbehave, and we really want to revoke you. So it's we cannot just avoid the problem of revocation just by using expiration dates. But it's a way to at least kind of reduce the.
Yeah, I guess I'm just thinking on like the web with TLS certificates, that's a much easier setting. We still haven't really solved revocation and basically rely on timeouts.
Yeah, and we can talk more. We actually have some discussions with people who work in the space that build things like CR Live, based on Bloom filters. So I can tell you more. We have some discussions. I mean, irrelevant anonymity, just like.
Okay, well, I have a second question, which is in a totally different direction. When COVID came out and people were talking about vaccine certificates, like initially the anonymous credential crowd was like really excited. This is a good application. Do you know if that ever went anywhere? Like, was there any polity that said like, let's actually try this? Or?
That's a good point. I think at some point most of the research actually shifted towards tracing, like privacy preserving tracing.
The traceability, but for like my New York.
You're right. I do remember.
Credential.
I do remember talking about this like vaccine credentials. I don't know what happened. I would guess if something happened would be in Europe. Sarah, you are aware of anything?
Did we miss the greatest opportunity to push anonymous credentials?
Yeah, well, again, I think that the focus kind of really shifted on the anonymous tracing. So, because that was what was really being implemented, I guess most of the people kind of.
Yeah, I guess in retrospect though, like if we had another pandemic, we sort of decided the anonymous tracing is worthless, but
Yep. So maybe that's going to be the opportunity.
Yeah.
All right. Thank you, guys. So I'm sorry.
There might have been one.
Oh, yeah, okay, cool. So somebody was talking about me, very nice. A mixed net which offers network layer privacy, good, and then coconut credentials got privacy. Okay. The idea with the, Anya, if you're still here and you want to unmute and tell us more about me, I'm more than happy to hear. I don't know if it would sound good.
Should make sales.
What's that?
It should make
Yeah,
sales.
sorry.
Yeah.
All right. Oh, okay. Yep.
I jumped my credential from my New York one and my Australian one. They both have like a digital signature. So it's not like
They're not anonymous, though, right? They don't have any privacy.
there's some crypto involved.
No, not really. I know them, but I never really. We had some discussion at some point, but it was not a time that I had time to
Right.
talk to them.
I could try to find.
Yeah, we'd be happy to talk to them. Are they under the protocol? Yeah, I think, yeah.
I think like Canada may have actually done something related to because the Sovereign Foundation